And fine. I have no idea what I'm going to do this week. I didn't prepare, so that could be interesting. I've got a bunch of graphs in here. Let's go and have a look for one. So let's see. Actually, I think I'll do one of the NTSF, the normalized tunable sigmoid function. So this particular thing I'm going to show you has its origin in around the early 2000s-ish, when I was working on one of the football games that didn't get published. And hey, Zagu, how you doing? I was working on one of the football games that didn't get published. And what I was interested in particularly was a thing I really wanted. I wanted to have a function that for an input of 0 gave 0, and for an input of 1 gave 1, but yeah, shoulder's okay. I can even put it behind my back now. Sometimes it twinges a bit, but yeah, and I can play my musical instruments. It took a good few days. For the first few days, it was a bit scary because I literally couldn't do more. I couldn't lift my arm. I couldn't lift my arm off the table. It was like, it's just. But yeah, it's coming back. Anyway, so normalized tunable sigmoid function. So what I was looking for was a function that would give an input of 0. For an input of 0, give an output. Let's just mess around with it. I could just show you it, but why don't I could just mess around and see if I could recreate it from memory the way that I recreated the function. It's a good exercise to go over the process that I went through, and then I can always look at it. Well, yeah, jump to the end if there's an issue. And what I liked to do was I liked to use this in my course because when I was teaching, because it was so incredibly useful, and it still is incredibly useful. In fact, it gets used by people. It's like a little bit of research. I put it up on my blog when I had one, and it finds its way into a few places. I'm quite pleased with the thing. Now I like to say, well, it's my thing, and still after some 14 years, well, maybe 13 years since I made the course material, maybe you find something. There are things called smooth step functions. There is a thing in one of the graphics gems books which doesn't show this. It shows something very similar. This is a kind of, I call it a normalized tunable sigmoid function, but it's probably closer to a smooth step function, or maybe, but it's more versatile. So anyway, I'll just go through the thing, and we'll see. So, but I'll take us through it with some of the theory about what the hell this is for. I could show you it, but what's the problem I'm trying to solve? So, in the football game, I wanted to have something that controlled how hard the ball was kicked, depending on how fast you were going. Now, you could think there are different ways of doing this. I'll show you a very classic way, and we'll do it with a graph. So if I just sort of put x in here, I'm actually plotting y equal x. And maybe if I switch this to sort of projector mode, you can tell me if you can see, if you can read the writing. If you can't, I'll make it a bit bigger. Okay. So what we could say is that the x-axis represents how fast the football player is running. And when the football player hits the ball, then we want the ball to get kicked forward by some kind of impulse. And the faster that the player is running, the bigger the impulse should be, which kind of makes sense, right? So of course you start off naturally with a straight line, and this is pretty much how everybody thinks these days, which is fine, but it is not very sophisticated. We can be more sophisticated. I'm going to start off with a very simple thing. So if we normalize the speed of the player, that is, change the speed of the player to a range between 0 and 1, where 0 is presumably standing still and 1 is moving at a certain maximum speed, if you will, we could do a relationship like this. So this is 0 here is the slowest speed of the player, and 1 here is the highest speed of the player, right? And then we could also have the force with which the ball... Hey Mycon, how you doing? Good to see you. We could have the force with which, or the impulse with which the ball is kicked forward, also between 0 and 1, where 0 is the smallest amount the ball is kicked forward, and 1 is the maximum amount. And then, hey, you just connect the two. You can use in Unity the lerp and inverse lerp functions. So I tell you what I'll do to do this. I'll just sort of set up that framework a minute. But we'll need a few variables. First of all, let's have the minimum speed that the player can run. Good to see you too. Let's move the minimum speed. So what I'll do is I'll call that, say, P M. This is the player minimum and maximum both begin with M, which is really annoying. Min. So P min, and we're going to say P min is, oh well, I suppose it's 0. And then we can have P max, which is, oh, I don't know. Now we could say the player could run as fast as, let's make it simple, 10 meters per second, which is actually pretty fast. It's like 10 meters per second would be, you know, just about the speed, a little bit less than the speed required to break the world record at 100 meters. There's some maths there. It's 10 meters per second multiplied by, well, 100 divided by 10 meters per second is 10 seconds. But let's go with it. And so if I have that, then what I want to do is also have a slider for the current player speed. I'll call that P speed, and I'll set him equal to 5. No, that doesn't work. I have to equal 5, which is fine. And I'm going to plot that speed. Well, backwards is just the same. It's the same as forwards, but in a different direction, really. So I tell you what. Let's plot the player speed as P speed, comma 0 here, and then here you can see this is the speed. Oh look, he is running backwards. So I tell you what, we can clamp the limit here between 0 and 10. There we go. So this is the range that we can have the range like this, right? So that's the speed of my player. And what I'm going to do is normalize this. So what I'll do is put player speed P speed N. We use an underscore to get that kind of, you know, that notation there. P underscore, and you put a subscript. So P speed N, which is the speed normalized. And so what we want to do is take, this is the inverse lerp function, right? If you do math inverse lerp in Unity, it basically is a one-liner. So I'll just, yeah, we are. People call it, I called it the normalized tunable sigmoid function. You will see why. Because it's an infinitely tunable smooth step. Yeah, it's actually, so what I'm going to do, well, if you could call it a crossfade, I suppose. Right, so what I'm going to do, depends what you use it for. What I'm going to do is do the inverse lerp. So let's just think about how we do an inverse lerp. What we want is when the speed is 0 or at P min, then we want 0, and when it's at P P max we want 1. So it's actually really simple. What you want to do is see what your speed is relative to P min. So that's your speed minus P min. So I can do speed minus P min, like so. And that needs to be divided by the range, the full range that's possible, which is max minus min. So this is very standard kind of arrangement. We do P minus min. Now, at this point, it's drawing all kinds of weirdness here. I don't know why. Speed is fixed. That's kind of cute. I have no idea why it's drawing that. I don't really want that. What I'm going to do is plot the speed normalized on the it doesn't know speed P min, that's why. Probably because I misspelt it. P min. Oh, I made it lowercase. There we go. That's why it was plotting that graph. So what we should do is have this now. If I slide, you can see how this works. This is. Let me just turn that off a minute. No, not that. Turn that off a minute. You can see that as I go to 10, that's a value of 1. That's on 1. And then 0. So this is the inverse lerp function. It's really, when you go into Unity and do inverse lerp on a float, and basically it's just done that. Except that it does also clamp it. So really, let's see. If I want to clamp it as well, which do I want to clamp it? Yeah, right. So what I can do is do a clamp by saying the minimum value between that and 1, and then say the maximum value between that and 0. It's a little awkward, but that should do it. So this will actually clamp the output. So if I allow it to accept to play a speed out of range, let's say Mycon's negative speed, or there, from -2 to 12, you can see it's clamped. Well, you see on the blue thing there, it's clamped. So now that's exactly the same as Unity's inverse lerp, which also clamps. So of course I can set the minimum to be something else, like 4. And now when this reaches 4, we're at 0 and clamps, and then it goes to 10. Between 4 and 10 we have that range. So that's all very well and good. I think for convenience sake I'm going to take this and turn it into a function. So I'm going to call this function f inverse lerp, which will take as its argument x, and then I just need to put that in there, and now I can say p underscore speed n equal my inverse lerp of p speed. Should hopefully restore it. Something went wrong. Let's see what it doesn't like. Subscripts may only contain, okay, I have a weird character in a subscript, clearly. Oh, yeah. It's annoying when it does that. There we go. So what's nice about it is now I have taken my lerp function which I can tweak, the minimum and the maximum here, right? And I have it in a function, which means I can plot it. In fact, if I just turn this on, we can see a nice plot of the input of 10 gives me an output of 1. That's that purple line is showing you the plot. The input 0 to 10, output 0 to 1. And if I tweak my minimum and maximum values, as you can see, look, so this makes sense, right? So in fact, this is a step function. If you can see that, it looks like you can think of it like that, but it's not really a step function. A step function would be completely vertical here. It's a kind of smooth step, isn't it? It's kind of interpolated step. You may not have thought of the inverse lerp function as being a kind of a step function, but in fact it is. With an interpolation in the middle, you can give it a range. So if I say the minimum value is 2 and the maximum value is 5 of player speed, if the player is going at less than 2 meters per second, my normalized value for speed is then 0, and above 5 it's 1. And so that might be good, right? Because I can use that to then instruct how the ball is kicked. Okay, so the second stage of this is then to use a lerp. So this combination of an inverse lerp and a lerp is something I like to use a lot. It'll allow you to map one range to another, so that you can then say, if the player's speed is 2, the kick amount is, 7. If the player speed is 10, the kick amount is 8. And then you can tune those parameters. So I'm going to do that as well, might as well while we're here. So these are the player minimum speed, which I'm going to set to 0. Maximum speed, I'll keep it at 5. And then the current player speed then is going to be, 2. Oh, say 5, sorry. For the maximum, and the current player speed is going to be 2, and if the player speed is 2, then the normalized value for the speed is 0.4, which is there. Oh, that's cool. Now we need some more sliders, because I want to map this the other way. I've got a normalized value for the player speed, but I want to now convert that normalized value of the player speed to a normalized value for the amount of kick. Well, actually, you don't need to convert it. That's the beauty of... I have the wrong category again. Oh, emergency category change. Thank you. Let me just fix that. I should have different channels or something, I don't know. To each. So can I go to my channel, please? Let me just fix this. And down here we're going to do the flipping edity thing. And now the category is mathematics. No, I can't. Mathematics, I can't spell. Where is it? Math. Oh, because it's an American site, therefore it's math, not maths. Math workshop. Maths. Okay, there we go. That should do. Alright, so what we're going to do now is have the amount that the ball is going to be kicked. I'm going to set 3 well, two values for it. Because as I was saying, I don't need to normalize the kick value. It's driven from the player speed, right? What I do need is to have what a 0 for that player speed means and a 1. So that's going to be k-min. And so we'll say k-min is it kicks the ball when the player is running at 0, it kicks the ball at 0 meters per second. And and when for k max the maximum kick is, well, let's think about it. Well, if I'm going at 5 meters per second, let's call it 6, because I mean we want the ball to get kicked a little bit faster than the player. You see what I mean? So if we set this parameter up, these parameters like that, now I need to have the lerp function, because we had an inverse lerp here. I'm going to set up a lerp function. So I'll do it straight in here, f underscore lerp, and we're going to go lerp x. And so what's the inverse lerp? I mean, what is the lerp? The lerp is very simple. If it's 0, you want A, and if it's 1, you want B. How can you do that? So you start with A, and maybe you add the t value, which goes between 0 and 1, multiplied by the range, like this. So you go kick min plus, and this is a very common pattern, the difference between the two, which is k max minus k min, and multiply this by t. Actually, I need to have, I'll call this t, it's often used the t value, times t, which has plotted me another graph. And yep. Well, in the end, a crossfade is really just a function of lerp. I mean, you can use a lerp to do a crossfade. You have a number between 0 and 1, and then you specify how 0 is black and 1 is yellow. If you want to crossfade with another color, you just set up 2 of those, and then you have the start and end color for the both, and then you know they both start yellow. One starts yellow and the other ends yellow. So basically, if you do that, then you can just scrub between them, and it will just blend between the 2 colors. Actually, you probably don't even, no, you don't need it to start with the same bit. You just have 2 colors. You have one red, one blue, and it just will fade between. In fact, actually, you don't need 2 of them. You can just literally, I was going to be complicating it. You can literally have red on one color, blue, and you slide between red and blue. Right. Internally, that's kind of, never mind. So what I'm going to do is then, as I change the player speed here, right, you see that blue dot is the normalized. I tell you what I'll do is I'll plot that normalized on the other. I should visualize it quite well. Speed n. And now, just so that you know, one of the things that we can do is on this thing here is I can hit play, and maybe we'll, so I set the maximum to 5, we can just sort of have it do this. Okay, you can just see it sort of like the blue dot is the normalized value for the input speed, and I've just reproduced it here with this red dot here, which I'll make blue as well. So this basically, these two are the same, right? They're just on a different axis. And now on the vertical axis, I'm going to plot the amount, the impulse that's given to the ball. And for that, I need to use the lerp function, which I just made. is being plotted. I'll take that plot off. In fact, I'll just take this off for a minute. So to do that, I need to set it up so that the kick speed is equal to f lerp for the parameters which have been set up here, for the t value, which is p speed n. And so now we can see that there is a speed value changing here. The speed value is changing, and we'll plot that, and I'll plot this one as a red. So this will be 0, k speed, and now you can see the green one there is how much it's kicked for the different speeds. Of course, I can plot that graph out. Can I? Yes. To plot it, I would need to plot if I want to plot x against y, which I'm kind of sort of doing here, it is this. It's the f lerp of f inverse lerp. This is exactly the equivalent of what I do in code, actually, for x. And there you can see that plot is showing you the curve relationship between the speed of the player and how hard the ball is kicked. Of course, it's done in a very general way. The problem is that this doesn't give the good result, because when you try it, you just find that the ball gets kicked away too much, or sometimes is a bit sticky, and maybe you want to have just a little bit of a minimum. I mean, we can add a minimum force, so even if the player is staying still, he just touches the ball, it kicks the ball a little bit. So what you do at this point is when you set up this kind of thing, is you then start experimenting, right? Tuning it. And so you might go and say, well, I know that the player speed is a minimum of 0 and the kick, but I want to have a minimum kick value of a half. So then we do this, and so now you can see that the lowest amount that the thing will be kicked is 0.5 meter per second. And then you say, well, you find that when he's running at 5 meters per second, the ball is going too far away. So what do you do? Okay, so we'll pull it down then. So we'll pull this down a little, say to that, so it's 5 instead. But the thing is now it's 5 when it's 5. So now that's actually not getting kicked. So maybe it needs to be 5.5. And so you might settle with something like this. And so this is a fairly standard thing that you do for tuning some kind of relationship between two things. But it's inadequate because it still doesn't quite work. And so what I was doing, I was thinking about this and going, I really wish I had a tunable curve. So maybe it would be nice if I could have it, but it would do this kind of thing. Because it could be that in here, when we're in the middle range of the player velocity, which is here, because this is what I'd find. Maybe I was happy with this, and I'm happy at this point, but when I'm about halfway, it's like too close, sticking to the player. And so then you go, well, I need some other kind of relationship here because a straight line isn't enough. What I want is a curve. So I went looking for the curve. This is way back soccer 2 time, when I was working at Precision. I can remember that this is when I started working on this, trying to find an answer. Wouldn't it be nice if I could have a function that if I input 1, 0, I get 0, and 1, I get 1, but I can change the curve, so I can change what the value is at a half. Maybe do this, or this, or this. And so I set off to try and find a solution for that. So I don't know if I can. I'll have a go at trying to recreate such a function from scratch, from memory. I know what the formula is, but I'm just curious about the process. How would we find something? Because that's more interesting than the actual formula. I found one. I created a version of it which was simple, but a little inelegant in use, and then I actually created a newer version, which was the one I use these days. Very simple, though. I wanted it to be simple. I didn't want it to have an exponential function, because that's the first thing you will think, isn't it? You go, oh, I know. Look, this function that we have here, because it's useful when you create an inverse, because a normal, when you normalize it, because a normal value between 0 and 1 has great properties. For example, if you square it, it still stays in the range of 0 to 1. And so you think, oh, okay, let's do that. In fact, I can show that here if I just put this in. Now this, let's hit play. That isn't quite what I expected. Let me just check something here. The inverse lerp. Let me put this back. Inverse. Yeah. Because it shouldn't. Yeah, that's a bit weird that it did that. Because in theory, I should be able to square this. Oh, there you go. And then as I change. Because, I'm changing the wrong value. I'm changing K max. I don't want to change K max. So what was that? It was 5.5. Now there we go. I hit play for the wrong thing. No wonder it was confusing you. There we go. So now the graph, but it's not showing that for the movement of the green dot, because for that I calculated it separately. So it's the left of the speed normalized. So I need to square it here as well, I think. All right, that's better. So, remember the red is the speed of the player, and the green is how hard the ball is kicked. So at least I've got a curve now. I mean, it's still the same for the beginning and the end. If I'm at the minimum speed and the minimum speed is 0, if I'm at the minimum speed of 0, then I get the output speed of 0.08 actually at the moment. And if the input speed is 5, then I get the maximum of 5.4. So it's great, but I have changed the shape of the curve, which is fine. So then, of course, you'll say, well, but this is kind of hardwired, isn't it? So wouldn't it be good if we could just sort of change that? So I'm going to show you this now in a separate graph, because this is all getting a bit confusing. I'm going to just simplify the focus to the range between 0 to 1, because that was really demonstrating the use of normalized values. So I'm going to go from 0 to 1, and I'm going to hit X, and now I have a function that goes from 0 to 1 on the X, output 0 to 1 on the Y. Right. So x equals 0 between the range of 0 and 1, and I'm going to create my function which takes a value of x, and it's equal x. I'm just going to obviously make that more complicated in a minute, just to help me explain what I'm doing. And then I can do f of capital X, and now that moves according to the function. If I hit play on this, that's fine. Then I can show that as x comma 0 on here, and then I can also show and do a similar plot that I did before. That didn't work. Why not? There we go. Ooh. So there we are. So now we've got an input and output relationship, as you can see. And for this plot here, I'm just going to make it that the range is x is 0 is less than or equal to x is less than or equal to 1, and so it's just crop that plot. This one is just, you know, clamped or limited to the range of 0 to 1, and there we are. That's great. And so now if I modify my function, which is this guy, if I modify this function, I can say squared, and now you have, so this might remind you of something. It might look a little bit like a gamma function, because you want a curve, right? There, 0 to 1, yeah. Put it on a power, you know. So we'll do that, and I'll call this P. I had a slider for it, and now I've got a tunable thing. And well, we might need to put a range on this. If I put 0, oh, okay, 0 is not very good. How about 0.1? Oh, okay. I'll allow 0 to sort of 10, maybe. We'll see. Yeah. Ah. And so you've got, and you say yay, but we're not really, yeah, it's not entirely ideal. It's not very symmetrical, first of all. I mean, the angle here isn't the same as the angle here, and maybe you'd want it to be. The other one is that because of the nature of this is a power of, well, 2.7. When you get close to here, it's very small. This is practically flat. And maybe you don't want it to be flat. Maybe you want some kind of give in there. But for some functions, for some purposes, this is totally adequate. There's another problem with it. These powers, taking a number to a power where that power is afloat, that is slow. It's a floating point function that is not instantaneous to calculate. You can definitely use it, and these days strenuous efforts have been made to make that as fast as possible, but it's nowhere near as fast as avoiding using a mathematical function. So my solution, you have no need for that. How is that? Let's see if we can get there. But this is, other than that, this is kind of what I want. It's like I'd like it to be able to go up here and down there. Oh, and a value of 0, it's kind of goes sort of flat. But at least at a value of 0, you know what that is. What about the other end here? This is 10. I mean, I suppose you could go, oh, right, 100, 1,000. I see. So to go the other way, you would need an infinite value. So the range for this as a tuning parameter is not particularly elegant. It's like it's unbalanced. On one side, you have a good control with small numbers. On the other side, you're having to go up to, you know, you can see here as I sort of, that slider is moving linearly, and you can see the effect. So there are some things that are not ideal about it. It's not very performant, it's not very elegant, it has a problem with the slope, that if I really want to sort of pull, if I want to have a steepness here, then I end up with flatness here, and that's probably not what you want, and so on. Okay, so I rejected that, because believe me, it was the first thing I tried, and so that wasn't really giving me what I wanted. So let's see if we can try something else in our function. So I'll take this and put this down here, and is equal x. There we go. So the thing then was to think about this is, I know that when it's 0, right? You think of the two endpoints. When it's 0, I want 0, and when it's 1, I want 1, and I want a curve. So the natural way to get a curve, other than using a power, right? I don't want to use a power because I've just tried that, but I do want a curve. So how do you get a curve if how do you get a curve without using a power and without using any mathematical function? I mean, ideally, I just like to use multiply, divides, addition, subtraction. And so that's what I started thinking. Let's have a look at. Ooh, I like these. This is nice. Look at that. So this is like a spline. This is from Micron, wasn't it? This is. It's like a spline, isn't it? It looks like a spline code. So when you're looking at spline, yeah, you can see this is pretty complicated code. But yeah, it's nice, and it certainly has its uses. It's a Bezier curve, yeah. So you can definitely use these if you want. I mean, I could go and we can try it and have a look at this. But it's a little bit overkill for what I was looking for. I wanted a single number that would affect the curve. So here I'm trying to set this up for... Now, admittedly, if you use a Bezier curve to solve this problem, you get a huge amount of control. But it's not without certain issues. For example, that. So for an input of 0.9, which value am I supposed to get back? Because there's 3. 1, 2, 3. The thing to remember about a Bezier curve is misleading because it looks like you've got the plot. It's like what you need. But the thing to bear in mind is that it's a parametric plot, which basically means that I don't know if this thing here has a way of P. There we go. So that is the value that's going between 0 and 1. And as you see, it speeds up here. So if I was to take, say, this shape and say this is the curve I want, the first thing I would have to do is take the input value of 0.2. I would need to find the p-value at 0.2, which is 0.15, and then read back the y that I get for the value at 0.15. And so the problem is that you've got to have this lookup. You need to do a reverse and inverse of this to find the spot here such that you know the value of p that corresponds to one axis. So at first you get excited about this, but in fact, then you see how big this calculation is, and it's this. That's a lot of mathematics going on in there. Plus, you need to have the lookup as well. So definitely. Oh, sorry. You can't see it was off screen. Sorry about that. Yeah, this is the big function. What I was basically saying was that here you can see the p-value, which I suppose is like the t-value. This goes in a range between 0 and 1, but it isn't linear. It sort of speeds up and slows down. If you want to find the value when the input is 0.2, the first thing you would need to do is find the value of p for 0.2, which is about 0.15, and then put that in to the equation for the y-axis. And yeah, so long mathematical function, and you'll have to reverse it, do a lookup on the x-axis to then get the output on the y, which you could do, but it's going to be expensive. So what I was saying is that when the input is 1, the output is 1. I know that. When the input is 0, the output is 0, and I want a curve. So the answer with that is that there needs to be a divide. There just needs to be a divide, because that's the only way you can get a curve without using a power. So that was the first thing. In fact, there is a divide in the function. Second thing to think about is that if there is a divide, we know that there is a divide, then it's quite clear that to get 0 for 0, then we need to have x on the top. And so this is basically showing how you can use reasoning to construct this kind of curve. I like to do this especially because there was a student who completely and publicly denied that it was at all possible that I came up with this. I never forget. I never forget. It's a shame. I wish I did. I wish I could forget. These things matter, you know. Yeah, it is totally possible to come up with a mathematical formula. It's problem solving. So what you do is, you know there's a divide, and you know that there needs to be an x on the top. If I put just an x on the top, then I know I will get 0 for 0. Great. Now I need to figure out what do I do to get a 1 for a 1. So that requires a little bit of thought. If I divide by 1, I will get a 1 for a 1. But that's without a curve. So you know there has to be an x, because if I don't put an x on the bottom of the curve, on the bottom of the divide as well, I'm never going to get a curve, because I'm only going to have a constant at the bottom, and so then it will always be linear. So you know, therefore, from that logical reasoning, there has to be an x above the divide and an x below. Next question: if there is an x on the above and an x below, how can we get 1 for 1? So that's interesting. Well, we can get it if we do x divided by x. Let's try it. X divided by x. That's always 1. Oh, right. That gives me a 1 for 1. It doesn't give me 0. Yeah, it doesn't give me 0 for 0. It gives me undefined for 0, because I end up with 0 divided by 0. So I can't quite have that. Okay, so let's think. Well, the divide by 0 The divide by zero is something we can't have. And at the moment, it's a bit like a chess game, I suppose, isn't it? It's like there are no options here as we reason this through. I mean, like there needs to be an x on the top, there needs to be an x on the bottom, and there needs to be no possibility of a divide by zero if x is equal 0. So the only thing we can do is add a constant to the x underneath, at least to get rid of the divide by 0. So you try that. Whoa. You look at it and you go, that's cool. I got a curve. You see, you do. You get a curve. It's not a parabolic curve. It's actually a part of an asymptotic curve. If I tell it to just plot the whole curve, you can see the form of it. This is an asymptotic curve that as x tends towards infinity, this is tending towards some kind of value. So when I saw this, I said, okay, let's just play. Let's just play with this a little more. The exciting thing is that I got a half for 1. I want 1 for 1. Right? Just multiply it by 2. Oh, okay. So then we get the new form. This is 2x divided by x plus 1. And I have a curve. And look at this, it's a thing of beauty. Because it's symmetrical between the 0 and the 1. It is an asymptotic curve with 2 asymptotes. Well, I guess 4. As x tends towards infinity, y tends towards this value. But you can also equally say that as y tends towards infinity, x tends towards this value here. And that is all not very useful because it goes off to infinity. But what's interesting is there is a symmetry on a diagonal. And if I pin 0 to 0 and 1 to 1 with this form of function, I have myself a curve. That's got a nice shape to it. You can see it's like this angle. In fact, I analysed this at a later date and proved, it's not difficult at all, that this angle is the same as this angle. So that the slope at this point is the opposite slope to this. So, I mean, you can see this if I plot that. The blue line there is just the, you know, just the 45-degree line. You can see how nice that is. Right. So at this point, I get quite excited because I say, well, it's got to. This is it. Now, how can I vary that curve? Well, I've got a clue already. I mean, the key thing is that to make that curve variable, I've got to change some of these numbers. And if you think about it, the bigger this number is, because the number is 1 at the moment, if I make that number big, well, let's try it. So I make the number bigger. Okay. Then I need to make this number bigger. Oh. 2, 1. All right, let's try 3, and then we make this. Oh. It's more like, it's closer to being linear. And then you look at it and you go, there is a relationship here, isn't there? If I go this up to 5, then in order to get this, I need to make this 4, 4, 4. There it is. 0 is 0, 1 is 1. And I've got a curve, and the curve is more linear. It's a bingo. And actually, there we are. It wasn't exactly hard, was it? I know what it is. The parameter, which I will call k, should be that, except that didn't work. So now I've got to figure out why. So if k is 1, that's something I broke it. So let's figure out why. If k is 1, then I need to. It was k. Oh, minus 1. Between minus 1, and so then I played with it because it's kind of interesting. Let's do, say, between a range of minus 3 and 3. Oh, I had it on a value that was invalid, like k equals 0, it just disappears. But if k equals, well, yes, you can see how if k equals 1, then it's going to explode when x equals 0, which we had that before. So I think k needs to be bigger than 1. But if k is bigger than 1, then yeah, there it is. That's what I want. So it turned out that for a value of k greater than 1, you'll get a curve. Between 1 and 0, it would behave unpleasantly, incorrectly. But if you get back below 0, then you get another curve, and that curve is in fact the reflection. 3 minus 3. And providing you stick with, you don't put it in the range between 1 and 0, you will always get valid values. If you go into that range between 1 and 0, then this kind of thing happens, and so it's basically broken. Actually, interestingly, if you clamp it in that range, it looks like it just doesn't enter that box at all, doesn't it? See? So I was quite happy with that. And I used that version of the normalized, I called it a normalized tunable sigmoid function. Why? Well, because you can then make it work on both axes. So you can probably do that by doing this. And then let's just put the range in again. 0. Well, now I can go minus 1 less than equal to x less than or equal to 1. Because there's a really good application for this, which I will show you. I'm going to just change this, because there was another reason for this, which is joystick sensitivity. And so, and this k range, let's do minus 10 to 10. If you want to make it linear, you have to get a very large, in fact, you need an infinite value of k to get a linear line. But that is not, admittedly, even with 10 here, it's pretty straight, but there's a little kink to it. Right? But this gave me what I wanted, so I could put that curve into this thing, and instead of having, the issues that I had before, I can tune it so that I can say that, yeah. You can see how this plot there is, you've got the grey dot is the input value and the red dot is the output value. If that doesn't look quite clear, I can always do x comma f x. This makes it clearer, doesn't it? So what I did to make it work in both directions was simply use the absolute value of x in here on the underside here, and by doing that then we end up with it being reflected both ways, and so that's why I called it sigmoid, tunable sigmoid. Technically it's not really a sigmoid, and it's closer to a step function. You could look at it as being a smooth step function. If I take this value and make it, well, in fact 1, then it becomes a step. Boom. But unlike some other smooth step functions that you might look at, this one is actually really cheap because it doesn't have any exponential function. It does have a divide. That's the most expensive thing, is a divide. So I was quite happy with this, but then I wanted to take it further and figure out if there was a way to change the k value so that it was nicer, because with this I may have the ability to tune this, but k between 0 and 1 causes the thing to explode. That although I can get it to do a sharp step at the limit of -1 and 1, 0, sorry, and 1, at those limits. If I want to go to a straight line, then I have to put an infinite value in, which means then using it in code, I might in the end want to turn it off. I would really like something better than that. Now I'm not going to go through how I work that out. That was a little bit more involved, but I'm just going to jump to the new and improved version of the normalized tunable sigmoid functions. So hopefully, but before I do, I just wanted to say about a use of joystick sensitivity. Now everybody knows about joystick sensitivity, don't they? If you play first-person shooters especially, is what joystick or joypad or even mouse sensitivity, whatever. There's a problem, and the problem is that if you you have to choose between sensitivity and speed. And many games to this day, they have the most simple way of organizing that, which is to just change the maximum rate of turn. So if you push your stick, paperweight, but you push your stick this way, and you turn like this. You do this way, you turn like that. Okay. But the problem is that you want to be able to turn quickly. So you do this, and now suddenly it's like this, but now you don't have any sensitivity in the middle. And so you know, I mean, maybe they've got a little bit more sophisticated of late. I wouldn't know, really. I haven't played those kinds of games recently. But really what you want is both, don't you? I mean, what you want is to be able to have precision, but full speed as well. How can you have both? Well, you're not going to get it by just playing with the limit, trying to make the slope, try to change the slope of your graph, right, to change the sensitivity in the middle, because then you will end up changing the speed at the end. Let me plot that, and maybe it will make sense. So what I'm going to do is create a new function called j. The function j is going to be my joystick function, and its job is to map the normalized input of my controller from +1 to -1 to a normalized rotation. So that's how fast you rotate. Okay, so presumably rotation of 0 means you don't rotate, and a rotation of 1 means you rotate at the maximum speed, whatever that is. Okay, and so that's going to be my function j. So jx will take this value between 0 and 1. And if you just go and say x, then you will get this plot. And I'm going, which it's not very surprising, and we're going to go in a range of -1 less than or equal to x less than or equal to 1. So here we are. And so the sensitivity calibration that they will put, usually, that are put into these things, involves the simplest thing: you scale it. So what you do is you say there is a sensitivity which I'll call S, right? That sensitivity factor, and we'll just say the sensitivity factor is 0.5. And what you're trying to do is to get this slope here less, to try and get it less steep, right? Because I mean, yeah, let's try and do it. Say, oh, what happened there? Say 3. No, 3. That's better. So, right. You know, we could look at this and say that the output speed is clamped 0 to 1, but if I take that and plot, say, that j function times, say, 5. No, that won't work. Jx times 5. I can just do 5 times, like this. And then I'll set the slope equal to 1. For an input of 1, we've got a rotation of, what, 5 degrees per second, all right? For an input of -1, I've got a rotation of -5 degrees per second, okay? And now that's pretty fast, but the problem is that in the center, it's not very precise. So people want precision so they can aim properly. So what you do is you change this S value down. So if we bring it down to, say, 1/4, 0.25. Now we have more precision in the middle, but the maximum rotation speed has been severely reduced. It's now 1.2 instead of 5. There it is. What do you do? That sometimes one of the things they do is they put step functions in there, but those are really nasty because you then have to feel for where it is between one and the other. It's like really what you want is smoothness. We like smoothness. We understand smoothness. Okay, so this is where you can use my function, because bring this back. If I change this k value to be like this, you get the best of both worlds. And look at that. It's basically 1 multiply, an addition, a subtraction, a divide, and an absolute. That's it. You put that, and now you can tune, by changing the k value, you can change the sensitivity in the middle and still have full range. That's very precise, right? Lovely. If you were to try and do that with the other method, you would be looking at a rotation speed of 1/10. So hopefully the value is clear. So I wanted to show you this NTSF, normalized tunable sigmoid function is what I call it. And I'm going to show you there it is. I'll start a new sheet. This function here, let's go projector mode, it's a little more complicated, for sure, than what we had before. A little more expensive, but not much. At the top, we basically x minus x times k, which you could also write as x times 1 minus k, if you like. So there's a multiply and a subtraction. Underneath, you have a subtraction, there's an absolute, there's a multiply, and there's a plus 1. It's not really not very much different. But it's very much better, because if I go and say fx k1, I'm going to plot that. I need to have a k1 value, and why doesn't it like that? Function, oh, NTS, sorry. Yeah. And valid range of k is between -1 and 1. And I'm plotting the whole thing here, so it gets a bit confusing. But just remember, the valid input range is only between -1 and 1. So let's do -1 less than or equal to x less than or equal to 1. And see, that is behaving in exactly the same way as the previous function, except that the value of k is much better behaved. A value of k of 0 gives you a straight line. So I like that, because, yeah, straight line's good, value of 0, no infinities. The other thing is the entire range from -1 to 1 is valid. If you hit actual -1 and 1, it is kind of valid, but you end up with like divide by 0 or 0 divided by 0, and so I would actually say that the valid range is less than -1 and greater than -1 and less than 1. And maybe we could reflect that by doing this as -0.999 and 0.999, and now there you get this. If you use that kind of curve for your joystick input, you can get this nice precision without losing range. You could also go the other way, which is kind of interesting. Sine wave music. Aha! Well, you could use this for acoustic distortion. It's something I've been meaning to try out. In theory, you could. But yeah, you could go like this. And why would you? There is an argument in some experiments I've done. There's an argument for saying that in a racing game you might want to do that, so that you actually, which is, it sounds counterintuitive, but in the center you get, you know, but then when you're doing when you're taking a bend, you actually probably want precision, greater precision when you are on critical terms. So there is, at first thought, you'd think that you would never use that form for an input control, but in fact, actually, you might. You might actually. And the great thing is you can just try it between the two. Then there's another thing you can do with this, because of course, if you're looking at that and you go, okay, now wouldn't it be great if I could shift this sort of over or up and down, like the center point? It'd be great. So what I did was, this is the NTSF3. This is, yeah, a lot more expensive because it's 3 NTSF functions put in a chain. So it's actually in the end represented here by this hideous thing, which looks complicated, but really isn't. It's taking the x value between 0 and 1 and pretending that it's between -1 and 1 and feeding it into the NTS function, and then converting it back to feed into a second, converting it back again to feed it into a third. So what you end up with then is 3 k values, and let's see if I can NTS3. And I love this. I use this for things. Right? I use this in Necessary Evil, that experimental game I did a few years ago with Stefano Guellini. I remember using it for the sound of the army as it came faded in and then faded out, because you get full control over. Hi Bleman, NTS is normalized tunable sigmoid, which is just the name I gave to this function. Originally, did I lose it? Where did it go? The simple one. I seem to have lost the simple one. Never mind. You have a look at the video. But anyway, the first version of it, which I worked through the theory of how I came about that. This is the improved version, but it's yeah, normalized tunable sigmoid. So I call it that because you can see here it's a kind of sigmoid. You get 0 for 0, 1 for 1, -1 for 1, -1 for -1, and you can tune the shape in between. And so what I've done here is I've got 3 of these put together. Now, if I set all 3 to 0, I will get a straight line, and I can show you what the behavior of this is. Right? So if I change K2, you can see here it's just the same as what we had before. What gets interesting is that I can shift the input range. Basically, the input from -1 to 1 gets fed into a sigmoid, which drives this one, and then the output goes through a sigmoid as well. So if I change the input, you can see that we can pull this up, we can stretch this up or stretch this down. That gets a little clearer if I do this one. You can see this is really clear how this works. So for no matter, as long as you stay less than 1 and greater than -1, there is only ever one value, output value for each input value, and they stay within the range. But you can create all kinds of easing curves. This is one that's quite nice because it's effectively almost linear, and then just at the end goes. This one's quite good as well. This is the smooth step. This is using it as a smooth step, but it's a smooth step with a different characteristic at the top and the bottom, which is this. Plus, you can change where the step occurs. So these are very useful. You can just, I can get all three of them playing. So it's sort of cycling through all the possibilities. Yeah, I like it, it's fun. We could feed a sine wave into this. I wonder what that would do. Sine x. So this is a sine wave. What would happen if I fed the sine wave, which goes in range from -1 to 1, right? If I feed that into the normalized tunable sigmoid function. So what we could do, three-stage NTSF. This is interesting. Boom. And so I've wondered about what would happen if I sort of use this as a way of creating distortion. Because I don't know if you know about overdrive, especially for electric guitars or whatever, but you can really do a pretty good impression of that here. In fact, this, which isn't a three-stage, this is just really, these have been set to 0 here. So even if you just put a one-stage NTSF in here, you can see that as you pull this over, it becomes more and more like a square wave. This is soft clipping. I need to, at some point, I need to actually try this out and see what that sounds like. You know. So there's soft clip. This is called peaking. But you can. How to come up with? Well, that you missed the bit, but I showed the first hour. In the first hour, I showed how I derived it. At least the first version of this. So if you can just sort of, yeah, all of this would have different sounds. I mean, you would be listening to the same audio, but it's obviously getting distorted in some ways. I'd be really excited to try that out at some point, but it's like, you know, there's limited hours in the day. I never got around to it. So another thing I then used this for was dealing with AI in a football game, for looking at areas that a player would be interested in looking at to see if there's like an enemy player, and it's quite fun. So what I'm going to do is just try, I can duplicate the sheet. Oh. And that didn't really duplicate it, did it? Let me right, let me try duplicating it now. Okay, cool. And put in projector mode. Okay. So what I'm going to do is switch this to polar plot. And turn off this graph. Oh, I'll keep the graph on. Not this graph, no. I'll keep this graph on. Although that isn't really a polar plot that you're looking at there. And now what would happen if I drew a circle, but I changed the radius of the circle dependent on the angle, and change that relationship, right, by using the normalized tuning or sigmoid function. So for this, I'm going to first of all draw a circle by using a parametric plot. So cosine t, comma sine t, and I end up with turn that up a minute. I end up with this is the circumference of a circle of radius 1, but I've only drawn 1 radian. So this is an arc length of 1, because t is in radians and goes up to 1. If I go up to 2 pi, I'll get a circle. So now t is going in the range of 0 to 2 pi, and I get myself a circle. So that's cool. Now, if I was to multiply the sine and the cosine, whoa, hang on a minute, it's my phone. Get a landline, they said. It'll be fun, they said. It came with a package on the internet. Never use it, but it keeps falling on the floor. Anyway, right, so what I'm going to do is take this NTSF3 function and just, well, put it in here with a value of t, which, hang on, but before I do that, it'd be good to have t, because I need to have things normalized. It needs to be normalized. So let's keep t in a range of 0 to 1 and fix the circle by multiplying it by 2 pi in here. Right, now I've got a circle, but t is now in a good range. Actually, I changed my mind. Let's go from let's go from -1 to 1, and then I just need to multiply it by pi. And now I've got the full range of -1 to 1. Oh, that sounds good. And then I'm going to multiply the coordinates, the x and the y coordinates of my circle. I wonder, can I just do this by 0.5? Does that work? Unfortunately not. So I have to do the x and the y. They have to be done twice. So NTSF3 and we're going to put in here the t value and then the 3 constants, K1, K2 and K3. Ooh, intriguing. So maybe what I'll do is just set these to 0 to make sure that. Okay. I was hoping. Oh, right, yeah, because I'm changing the radius of the circle as it's drawn according to the angle, and I'm doing that in a linear way right now. It's a bit confusing. It's a bit clearer if I do that. I think I need to not have it go negative. So I could go from t 0 to 2, 0 to 2, and then in the NTSF function I could pass in t divided by 2. That's better. So as it draws the circle, it's making the radius bigger, and the reason why it's a funny shape though is because I only did it for 1 coordinate. Yes, that I can't. Yes, sorry. Ah, that's more like it. So now we've got the old spiral shelly thing. I wonder what would happen if I went back to the -1, 1. I'm just curious. If I go to -1 out of 1. Oh, we will get that. Okay. So, what will happen if I change? Oh. That's kind of interesting. I don't like the negative side. I'm just going to get rid of that. And now we've got to a half circle. I could always do -1 to 1 and then just put in the absolute value. Oh, that's no good. Hang on. It's absolute. Ah! Look at that. So what's going on there is that if I set these all to 0. Oh, come on. If I set this to 0 and this to 0 and this to 0, then you've basically got a cardioid shape. At this angle, the radius is 1, and this angle it's 0. This is because the angle is measured from 0 on this axis and goes to maximum here, right? And so that's where you get this fairly standard cardioid shape. But now I can distort the cardioid by using my normalized tunable sigmoid function. So what I'm actually, if I turn on the plot for that, where are you? Here, and change the color of that. The black plot there, I get put dotted lines. That black plot is basically showing the shape of the sigmoid. That is being used to change the shape of the cardioid. So if I do it like this, it becomes like a pointer. You kind of lose the cardioid sort of shape. If I tweak this one, we can, and so now if you ever want to do, this is very good for doing clock dial. Or heart generator. It's sort of definitely what the world needs right now. We have a heart deficit in the world. These are crossed. Ah, right. And if I pull this back, yeah. Can we make it thinner? Interesting. So let me see what else I've got. NT search. This is a really old one from like 2014. I don't really know what that is, but it kind of looks pretty. What else? Looking for other NTSF. We have this one. Oh, well, this was from 2014 as well. You've seen that just now, yeah. Oh, that's interesting. Normalized tunable signal amplifier, kind of smooth step function. Interestingly, the inverse of this function is simply the same function with k negated. Yeah. So if you apply the one with k negated on top of the one with k, then they cancel each other out, I suppose is the thing. That's probably from my courses. Experiment. I haven't looked at these in a while. What's this? I have no idea what that is. NTSF experiment. I don't know. Sine wave already had ease function. I already did that one. GTF 4. GT4 is one of my courses. So we're just showing the use of this for a joystick. Chain 3 NTSFs. So that's what I was explaining there is how you can put 3 of these together to create very flexible curve. Putting 3 of them together in code is really easy, right? It might look complicated, but it really isn't. NTSF. Oh. Here's one I did earlier. Joystick again. The red one there is the actual position of the input, and the black one is how it's interpreted after going through the curve. Super precision. Look how precise that is down in the middle there. Really precise. NTSF. I haven't looked through these in ages. We're at 2018 now. Oh, this is a taking the chain of 3 NTSF and then reflecting it. That's kind of crazy stuff. Alright, so again, not very complicated, but looks more impressive than it is. NTSF. And then this one, I think it was just some experimenting I did. Oh, right, yeah, it was just take the absolute value of the result, and then you can use this for, I was using this with shaders. So if you want to I take this off, you can do that. Say in a shader, as you're tracking how close a point is to another point, and you can use these curves to sort of affect how bright the pixel should be, or fragment, whatever. NTSF. So was that one? Yeah, I think we're there. So I think that's my lot for today. I hope that was interesting to you. And the next stream theoretically will be Friday if I don't hurt my shoulder or have some kind of accident. Be playing some live jazz again. So thanks for watching. Take care, everybody, and see you soon. Good night.